Welcome back to QHSE Talks, where we don't just talk about safety rules, we talk about how safety actually works in the real world. Let me start with a question every safety professional eventually has to answer, sometimes in a conference room, sometimes in front of senior management, and sometimes in a courtroom. When an incident happens, what exactly are you trying to determine? Are you trying to determine who messed up? Or are you trying to determine why the system allowed it to happen? Because those are very different investigations, and they lead to very different outcomes. This episode is tightly aligned with CSP-11 Domain 2, Program Management, and there's a reason the board puts this material here. Incident investigation is not a technical side skill, it's a management competency. In the CSP Blueprint, you're explicitly expected to determine appropriate incident investigation techniques, identify root causes, not symptoms, apply corrective actions that actually prevent recurrence, and use formal system safety analysis tools like FTA and FMEA. And that's exactly what Chapter 22 is about. But before we talk about tools, diagrams, and procedures, we have to talk about something more fundamental, how we explain accidents in the first place. Because for most of industrial history, accident investigation was brutally simple. Something went wrong, someone was operating the equipment, therefore that person must be the cause. Case closed. That mindset dominated early safety practice, early management thinking, and early enforcement. And to be fair, when systems were simple, that explanation felt sufficient. But as work environments became more complex, as energy levels increased, as production pressure intensified, and as systems layered technology, procedures, supervision, and management on top of each other, that explanation stopped working. Modern safety recognizes that accidents are rarely random and rarely the result of a single bad decision. They are predictable outcomes of interacting factors: human limitations, design decisions, environmental conditions, management priorities, organizational culture. And that's why this chapter matters so much for program management. Because Chapter 22 does two critical things. It traces the evolution of accident causation thinking, from blaming individuals to analyzing systems, and it gives us the investigation toolkit needed to turn incidents and near misses into learning, not repeat events. This is also where the blueprint's focus on EHS culture and leading indicators comes into play. If your organization only investigates injuries, you're already too late. If you ignore near misses, you're ignoring your best data. And if your investigations always end with retrain the employee, you're not improving culture, you're protecting weak systems. So today, we're going to walk through how different causation models would explain the same accident, how investigation techniques like FTA and FMEA expose deeper system failures, and why professional investigations focus on prevention, not blame. And to keep this grounded, because we're going to be throwing a lot of theories around, we're going to anchor everything to one simple scenario.
Okay, to make this concrete, because we're going to be throwing a lot of theories around today, I want to stick with a specific scenario throughout this deep dive.
Good idea.
Let's imagine a standard warehouse. We've got a guy, let's call him Bob. Bob is driving a forklift. He turns a corner, maybe a little too fast, hits a patch of oil on the floor, the forklift spins out and crashes into a big racking unit.
And the whole thing comes down.
Whole thing collapses. Expensive inventory is destroyed, and Bob, unfortunately, has a broken arm.
A classic industrial mishap. Unfortunately, all too common.
Right. Now, depending on which era of history you're standing in, the explanation for why Bob crashed changes completely. And that's really the mission for today. We're going to trace the evolution of blame.
From blame the person to blame the system.
Exactly. From Bob as a clumsy idiot to the laws of physics were violated, all the way to the corporate system failed Bob. And then Once we've done that, we're going to open up the detective's toolkit and see how a pro would actually investigate this whole mess.
It's a fascinating journey. It really is. From falling dominoes to complex logic gates.
So let's start at the beginning, the foundation. If you study safety, you cannot escape the year 1932 and a man named H.W. Heinrich.
Heinrich is the grandfather of this entire field. I mean, truly. Before 1932, if Bob crashed that forklift, the analysis was pretty much, Bob messed up, fire Bob.
Yeah.
That was it.
That was the whole investigation.
Right. Heinrich tried to bring some scientific structure to it. He introduced what he called the domino theory.
I love the visual here because it's just so intuitive. You just picture 5 dominoes standing on edge in a line.
Exactly. And Heinrich's whole point was that an accident isn't a single event, it's a chain reaction. One thing knocks over the next, which knocks over the next.
And he labeled them very specifically.
Very specifically. So the final domino, the last one to fall, is the injury. In this case, Bob's broken arm.
But the injury only happens because the 4th domino fell just before it.
Right. The 4th domino is the accident, the forklift actually crashing into the rack. And following the logic, the accident only happens because the 3rd domino fell.
And the 3rd one is the big one.
It's the critical one. He called it the unsafe act or mechanical physical hazard.
So, in our scenario with Bob, the unsafe act is him speeding around the corner, and the physical hazard is the oil slick on the floor.
Correct. Now, here's where it gets a little dated and frankly, a little controversial by today's standards. The 2nd domino, which causes the unsafe act, he labeled fault of the person.
Fault of the person. What does that even mean?
It refers to things like bad habits, carelessness, maybe a bad attitude, recklessness, character flaws, essentially.
Okay, so Bob sped because Bob has a fault. But what knocks over the fault domino? What's the very first push?
This is the wildest one, the first domino. Social environment and ancestry.
Wait, ancestry. Are you saying Heinrich thought Bob crashed the forklift because of his genetics?
It sounds absolutely wild to our modern ears, but yes. In 1932, the thinking was heavily influenced by the idea that recklessness or, negative character traits were inherited.
Or at least learned from your social upbringing.
Exactly. It was the nature versus nurture argument of its day. He was essentially saying, Bob is the kind of guy who speeds because he comes from a reckless family or a bad neighborhood.
Wow. It feels incredibly unfair. It's basically prejudging people, saying some are just born to cause accidents.
It is a product of its time, no doubt. But before we throw Heinrich out entirely, we have to look at his axioms of industrial safety because they genuinely shaped management thinking for the next 50 years.
And he dropped a statistic that, it's still quoted and debated today.
The big one. He claimed that 88% of all accidents are caused by unsafe acts of persons.
88%.
Mm-hmm.
So you're telling me that in nearly 9 out of 10 cases, it's the worker's fault?
According to Heinrich, yes. 10% were due to unsafe conditions, like a broken machine or a poorly lit area, and only 2% were truly unavoidable acts of God.
I have to push back on this. If I'm a factory owner in 1940 and I hear a safety expert tell me that 88% of accidents are caused by my workers being unsafe, isn't that just a massive free pass for me?
It's a huge get-out-of-jail-free card.
Right. I don't have to spend money on safer machines. I just have to yell at Bob to stop being an idiot.
You hit the nail on the head. That is the single major criticism of Heinrich's legacy. It allowed management to blame the worker almost exclusively.
We provided a perfectly good forklift. Bob drove it wrong. End of story.
Exactly. It focused all the corrective action entirely on the individual.
But Heinrich did give us a framework for fixing things, didn't he? The 3 E's.
He did. And despite that blame the worker bias, these are still surprisingly useful concepts today. The 3 E's are engineering, education, and enforcement.
Okay, let's apply these to Bob and his forklift crash.
All right. Engineering is the first and most effective E. This means you control the hazard through design. So for Bob, maybe we put a governor on the forklift's engine so it physically can't go fast enough to spin out.
You engineer the risk right out of existence.
You make it impossible to commit the unsafe act. That solves the problem regardless of Bob's so-called ancestry.
Okay, so that's engineering. What's the second E?
Education. We train Bob. We show him gruesome videos of forklifts tipping over. We teach him about friction and coefficients and why oil on concrete is a problem. We make him aware of the risk.
And the third, if education doesn't work.
Enforcement. The stick. We make rules. Warehouse speed limit is 5 mph. If Bob breaks it, we write him up. If he does it again, we suspend him. We punish the unsafe act.
The problem I see with enforcement, though, is that it usually fights against other pressures. If I'm Bob's boss and I tell him, drive slow, but I also tell him you have to move 500 pallets by noon or you're in trouble.
Which rule is he going to break?
He's going to break the safety rule to keep his job every single time.
And that's why Heinrich's model, while it was foundational, is just too simple. It treats the unsafe act as a choice made in a vacuum. It doesn't account for the pressures of the system itself.
There's one more thing from Heinrich we absolutely need to flag, though, before we move on. His definition of an accident.
Yes. This is crucial.
He called it an unplanned, uncontrolled event that could result in personal injury or property damage.
And the word could is doing a lot of heavy lifting in that sentence. A lot.
Right. So if Bob spins out on the oil, hits the rack, but the rack doesn't fall and he doesn't break his arm, he just sits there, heart pounding for a second. Heinrich says that is still an accident.
Yes. The dominoes fell. The fourth domino, the accident, still fell. The outcome, the fifth domino, was just lucky. This is so important because it shifts our focus from just preventing injuries to preventing the event itself.
Because if you wait for the injury to count it as a problem, you're already too late.
Way too late. You're playing catch up with tragedy.
So we fast forward a few decades. People in the safety world start realizing that maybe Bob isn't just a reckless guy with bad ancestry. We start looking at the brain. This brings us to part 2, the human element.
This is where we get into what's called human factors theory. It still acknowledges that, yes, Bob made an error, but it asks a much more interesting question. Why?
It moves from a judgment of character to a cognitive analysis.
Right, and the big concept here is overload.
I feel like overload is the defining condition of modern life, so this should be relatable.
It's the mismatch between a person's capacity and the load being placed on them. Let's think about Bob again. What is his load? It's not just the weight of the boxes on the fork.
It's everything else.
It's the environmental factors. Is the warehouse loud? Is the lighting bad, creating glare? Is that glare hiding the oil patch on the floor?
On internal factors, too. I mean, is Bob worried about a sick kid at home? Is he sleep deprived? Is he hungover? Is he stressed about money?
Exactly. All of that reduces his mental capacity. And then you have the situational factors. Is the boss screaming at him to hurry up? Is the deadline unreasonable?
So you combine high noise, low visibility, internal stress, and external pressure.
And Bob's capacity to process information just plummets. He didn't crash because he's bad. He crashed because he was overloaded. His brain literally did not have the bandwidth to process the hazard signal from the oil patch.
It's like when you're driving your car in an unfamiliar city and you're trying to find a specific address, so you turn down the radio.
It is a perfect analogy.
You're not deaf. You just need to reduce the auditory load so your brain can allocate more resources to processing the visual data of street signs.
That's it. And if Bob couldn't turn down the radio, the noise and the pressure of the warehouse, he missed the critical signal about the oil patch.
There's another model in this section that I really want to dig into, mostly because it has such a fantastic, catchy name, the Superman syndrome.
Ah, yes. This comes from Dan Peterson's accident-incident theory.
Tell me about this.
This is one of my favorites. Peterson was really looking at why people make a conscious decision to err. Why would Bob knowingly speed if he knows intellectually that it's dangerous?
Because deep down, he thinks he's Superman.
Essentially, yes. It's the inherent belief that I am invincible, or maybe more commonly, accidents happen to other people, not to me.
Mm-hmm.
Peterson argued that when you're operating under this syndrome, the decision to speed is actually logical to the worker.
Okay, you're going to have to walk me through that logic.
Yeah.
How is risking a broken arm logical?
Well, look at the inputs in Bob's mental calculation. Benefit. I get the pallet moved faster, the boss is happy, maybe I get to go to lunch a few minutes early. Real, tangible benefits.
Okay, and the cost?
The cost is a theoretical risk of crashing. But since I am Superman, and bad things don't happen to me, I perceive that risk as being zero.
So the math in his head works out. Benefit, high, cost, zero. It's a no-brainer.
Exactly. The flaw isn't in his calculation, it's in the faulty premise that he can't be hurt. Peterson also pointed out other things like ergonomic traps, maybe the forklift seat is uncomfortable, forcing Bob to sit in a way where he can't see properly.
But the big one he added was system failure.
Yes, he was one of the first to explicitly draw a direct line from the accident on the floor all the way back to the boardroom.
Meaning, if Bob has Superman syndrome, maybe it's because management never corrected him for speeding before.
Or worse, management actively rewarded him for being fast, for taking shortcuts. If the system's values, speed, production, numbers are in conflict with its safety rules, the system is actively designing the accident. The failure is at the top.
So we've gone from Bob has bad genes, which was Heinrich, to Bob's brain was overloaded, the human factors approach. Now, let's take the human out of it almost entirely. Let's talk about physics.
This is part 3, systems, energy, and behavior.
And this is the era of Dr. William Haddon.
A giant in the field. He introduced the energy release theory, and it was a radical shift in thinking. Haddon didn't care about Bob's childhood or his stress levels or his attitude.
He just cared about the physics.
He looked at the accident purely as a transfer of energy.
Energy transfer. Break that down for us.
Haddon argued that damage, whether it's an injury to a person or damage to property, is caused by energy. It could be kinetic, thermal, chemical, electrical, any kind of energy transferring to a structure, like a human body, in an amount or at a rate that it simply cannot tolerate.
So in our scenario, the crash isn't a mistake. It's a physics equation. The moving forklift has kinetic energy. When it abruptly stops by hitting the rack, that energy has to go somewhere.
It has to be dissipated. And if Bob is thrown forward against the steering column, that kinetic energy is transferred into his arm. If the energy exceeds the tensile strength of his bone, the bone breaks.
It's just math.
It's just math. It's not about blame. It's about forces.
This sounds incredibly cold and detached, but I imagine it's unbelievably useful for prevention. Because you can't always fix Bob's attitude, but you can always manage energy.
Precisely. Haddon gave us a completely different set of strategies for prevention, he said. Don't focus on the person, focus on the energy.
And his strategies were what?
Strategy 1, prevent the buildup of the energy in the first place. For Bob, that means limiting the forklift speed. Less kinetic energy.
Okay, makes sense.
Strategy 2, prevent the release of that energy. So better brakes, better tires with more traction, anti-lock systems, control the release.
And strategy 3, which I think is his most famous contribution.
Separate the energy from the person.
This is where barriers come in, right?
Yes. In a car, this is the seatbelt and the airbag. They don't prevent the crash from happening. They manage the energy transfer during the crash so it doesn't kill you.
They slow down the deceleration of your body.
In the warehouse, for Bob, maybe we put a heavy-duty steel guardrail in front of that racking unit. The forklift hits the rail deforms and absorbs the energy, the rack stays standing, and Bob, secured by a seatbelt, stays in the operator cage.
It effectively idiot-proofs the system. You just assume the crash will happen eventually, and you design the world to survive it.
That is the Haddon legacy. It's why modern cars have crumple zones and padded dashboards. It's not about making better drivers, it's about making crashes survivable.
But we can't completely ignore behavior, can we? I mean, at some point, we still want Bob to care and to try to be safe.
True, and that's where the final piece of this section comes in, behavior-based safety, or BBS. It sort of swings the pendulum back towards psychology, but in a much more modern way.
How so?
Instead of Heinrich's enforcement, which is all about punishment, BBS is all about positive reinforcement.
Ah, so catching people doing it right.
Exactly. You set up a system of observation. An observer watches Bob work. If he slows down at the corner and honks his horn, as he's supposed to, the observer goes up to him and says, "Hey, great job on using the horn. That's exactly what we need." You actively reinforce the safe behavior.
You're using psychology to make safety a habit, not just a rule you follow because you're afraid of getting in trouble.
It's about creating a culture where the safe way is the easy, recognized, and rewarded way to do the job.
Okay, so we have all these theories. Heinrich's dominoes, human factors, Haddon's energy, BBS. How do they all come together in the modern world? This brings us to part 4, the modern causation model.
The modern model is basically a root cause machine. It tries to synthesize everything we've just talked about. And the first thing you'll notice is a deliberate shift in the language we use.
Okay.
We don't say accident anymore, we say mishap.
Why the change? Is that just corporate speak to soften the blow?
It might sound like it, but words matter. Accident implies chance, randomness, bad luck. Mishap implies a breakdown in a process or a system. It's a much more accurate word.
What else changes?
We also stop saying unsafe act. The preferred term is now operating error, and we don't say injury, we say result.
Result. That feels very neutral, very scientific.
It is, because the result could be an injury, but it could also just be property damage or a near miss with no damage at all. It's just the output of the equation.
So in this modern model, if Bob has his mishap, how do we find the root causes?
We look for causes that go deep into the organization. The model gives us a hierarchy. At the surface level, you have the operating error. Bob sped, or he didn't look where he was going.
Okay, that's the obvious one.
But then you dig deeper. Was there a system defect? For example, the forklift's brakes were known to be spongy, but the maintenance procedure was inadequate.
So that's a failure of the maintenance system.
Right. And then you dig even deeper, was there a command error?
Command error. I like the sound of that. That puts the CEO in the hot seat.
It absolutely does. It forces the investigation to look at the decisions made by management. Did management cut the maintenance budget last quarter to save money? That's a command error that directly led to the system defect, which contributed to the operating error.
So you can draw a straight line from a budget meeting to Bob's broken arm.
A direct line. And finally, you look for safety program defects. Maybe the safety team knew the floor was frequently oily, but they didn't have an effective system for reporting or cleaning up spills. The program itself was flawed.
So the modern model says, don't just fire Bob. Fix the brakes, restore the maintenance budget, and buy a mop and create a spill response plan.
That's it, exactly. It offers specific countermeasures for each level of failure. If it's a management error, the countermeasure is training or education for the bosses. If it's a system defect, you need engineering to fix the process. If it's an operating error, maybe you need motivation or better assignment of staff.
It really feels like we've matured from just pointing fingers to actually fixing the machine.
That's the entire goal of the modern approach.
All right, so the mishap has happened. The scene is chaos. Bob is in the ambulance. The racking unit is down. Now comes part 5, the detective work, the investigation procedures.
And the very first thing to establish before you do anything else is the purpose of this investigation. And this is where I would say most companies get it completely wrong.
Because usually the purpose is find out who to blame so we don't get sued.
Or find out who to fire. And if that is your purpose, your investigation is worthless before you even begin.
Why?
Because the only valid purpose of a mishap investigation is to prevent recurrence. That's it. Full stop. It is not to exonerate individuals, it is not to satisfy the insurance adjuster, and it is definitely not to build a legal defense.
Because if you're just trying to defend yourself legally, you'll be motivated to hide the ugly truths. And if you hide the truth, you can't possibly fix them.
Precisely. So the alarm goes off, the call comes in. Step 1, secure the scene.
This sounds like something out of CSI. Are we talking about yellow tape?
Absolutely. Yellow do not cross tape. First, of course, you have to eliminate any immediate hazards, turn off the power to the forklift, shore up the rest of the racking so it doesn't fall on the medics. But once the injured are cared for, you must isolate the area. Barricades, guards, no one in or out.
Why is this so incredibly critical?
Evidence is unbelievably fragile. Imagine a well-meaning supervisor walks into the scene, sees the forklift's gear selectors in high gear, and instinctively flips it down to neutral just to be safe.
They just destroyed the single key piece of evidence that proved Bob was speeding.
Gone. Forever. Or someone from housekeeping rushes in and mops up the oil patch because they don't want anyone else to slip. Now you've lost the environmental cause. You lock it down. Only rescue personnel and law enforcement get inside until the lead investigator arrives and gives the okay.
Okay, scene is secure. Then you start collecting the physical evidence, photos from every angle, maps, sketches, measurements, and then you have to talk to the witnesses.
Witness interviews are the single trickiest part of any investigation. Human memory is not a video recorder. It's more like a Wikipedia page that anyone can edit after the fact, including the witness themselves, unconsciously.
The whole fragile memory concept.
Yes. If Bob talks to his coworker Steve in the break room for 10 minutes before you interview them, their stories will start to merge. They will unconsciously fill in gaps for each other. You need to get to them immediately and separately.
And if you can't interview them right away,
get a signed, written statement on the spot, even if it's just on a napkin. Write down everything you remember right now and sign it. You have to lock in that initial version of the memory before it gets contaminated.
And when you do finally sit down to interview them, how do you handle it? Bob is likely terrified that he's about to be fired.
You have to put him at ease immediately. The first words out of your mouth should be, Bob, we are not here to blame you. We are here to figure out what went wrong with the system so we can make sure this never, ever happens to Steve.
You're focused on prevention.
And you let them talk. You let them tell the story in their own words. You do not lead the witness.
So you don't say, did you see the big oil slick on the floor?
Never. You say, tell me about the floor conditions in that aisle. Let them offer the detail. Then, later, you verify. If Book says, I slammed on the brakes as hard as I could, but your physical evidence shows no skid marks on the floor, you have a discrepancy. And facts, generally, outweigh memories.
Before we get to the cool analysis tools, we have to touch on the things that didn't happen. The near misses.
This is arguably the most important and most overlooked data source you have. Heinrich, way back when, gave us the 129-300 rule.
I remember this. For every one major disabling injury,
there are 29 minor injuries, like cuts and bruises, and 300 non-injury accidents. Close calls.
But the modern stats from the book are even crazier.
They are staggering. Recent studies suggest it's more like, for every one serious or fatal injury, there are 59 minor injuries and 600 near misses.
600. For every one major event.
600. Now think about our forklift. Before Bob broke his arm, there were likely 600 times where a forklift slipped on a patch of oil, but the driver regained traction. Or 600 times a driver took that same corner too fast, but didn't hit anything.
Those are 600 free warnings from the universe.
They are free lessons. They are opportunities to learn without bloodshed. If you have a culture where people report and you investigate the near miss, the slip that didn't hurt anyone, you can find and fix the oil leak before Bob ever breaks his arm.
But most companies ignore them.
And most companies ignore them because no harm, no foul. It didn't cost anything, so it's not a problem. That is a fatal error in logic. You are just ignoring the hundreds of warnings at the bottom of the safety pyramid until the law of averages finally catches up with you at the top.
That is a chilling thought. Okay, so we have our physical evidence, we have our witness statements, we have data on near misses.
Yeah.
Now we need to process it all. This brings us to part 6, the toolkit.
This is where we leave gut feeling and best guess behind and use structured scientific analysis methods.
Now, a critique we've gotten in the past is that we sometimes just list these acronyms. So I want to actually use them on Bob's accident. Let's pick the big ones from the book and apply them.
Just do it. We always start with the basic scientific method. You form a hypothesis and you test it.
Bob was speeding.
Check the forklift's internal computer logs for speed data. Interview witnesses about his pace.
Okay, another one. Hypothesis, the brakes failed.
Test. Have a qualified mechanic perform a full inspection of the brake pads, the lines, the fluid levels. You try to prove or disprove your theories with evidence.
Simple enough. Now, what is GHA, gross hazard analysis?
Think of GHA as the rough draft of your analysis. You do this very early on, maybe on a whiteboard. You sketch a quick logic diagram. Forklift hit rack, why? Maybe excessive speed or slip floor or brake failure. It's a quick way to brainstorm potential causes so you know where to focus the deeper investigation. It's a broad brush.
Okay, then we have JSA, job safety analysis.
JSA is usually a preventative tool, but it's incredibly useful in an investigation. You take the written procedure for the job Bob was doing.
Inspect forklift to start a shift.
Pick up pallet from staging area.
Drive to aisle 4 and place pallet on rack. You look at the mishap and ask, did Bob skip a step? Did he not do the inspection?
Or, and this is key, is the step itself the problem?
That's the deeper question. Maybe step 3 requires him to make a blind turn into aisle 4. If so, the JSA shows that the procedure is flawed, not just the worker.
Okay, now let's get a bit more technical. FMEA, failure modes and effects analysis.
This sounds like engineering speak because it is. It comes from the world of engineering design. It focuses on the components, the hardware. You make a chart and systematically lists every piece of hardware involved.
So for Bob's forklift.
Item, left front tire, failure mode, worn down to bald, effect, reduced traction, especially on a wet surface, risk. High.
Hydraulic line. Failure mode. Cracked and leaking fluid. Effect.
Okay.
Creates a slippery floor hazard. Risk. High.
So you systematically interrogate the machine. You don't just say the forklift failed. You define exactly how each component could fail and what the effect of that failure would be.
Yes. It's a powerful tool that prevents you from missing a critical mechanical root cause.
Now for my favorite, just because it appeals to my inner nerd, FTA, fault tree analysis.
This is the big one. The logic diagram. With a fault tree, you put the undesired event, the big bad thing, at the very top of the page. In our case, forklift crash.
And then you work backward.
You work backward using logic gates. The two most common gates are AND gates and OR gates.
Okay, I needed a simple explanation of AND versus OR gates.
Of course. Think of an AND gate like a safety deposit box at a bank. To open it, you need the banker's key and your key. If you only have one, you get nothing. Both conditions must be true at the same time for the event to occur.
Okay, both have to happen. What's an OR gate?
Think of an R gate like your front door. You can open it with your house key, or you can punch in the code on the keypad, or you could, I guess, kick it in. Any one of those single events is sufficient to open the door.
Got it. So applying this logic to Bob's crash.
We might create a tree that says, the forklift crash occurred because we had an uncontrolled skid event. And the uncontrolled skid occurred because we had Bob driving too fast, Andy oil on the floor.
An A&D gate.
A critical Andy gate, because if Bob was driving too fast on a clean, dry floor, maybe he makes the turn just fine. And if Bob was driving slowly and carefully on the oily floor, maybe he slides a little but maintains control. But because both things happened at the same time.
We passed through the Andy gate and the crash occurred.
And that is so powerful because it tells you as an investigator that if I can remove either the speeding or the oil, I break the chain. The top event cannot happen.
You don't have to fix everything to prevent the accident. You just have to break the logic chain at one single point.
That's the beauty of it. Finally, there's MES, multilinear event sequencing.
What's that?
This is basically a timeline on steroids. You create a chart. The columns are time and the rows are different actors. Row 1 is Bob. Row 2 is the forklift. Row 3 is Bob's supervisor. And you plot the events. Time. 9:00 a.m. supervisor yells at Bob, "Hurry up, we're behind schedule." Time. 9:05 a.m. Bob skips his pre-use forklift inspection to save time. Time. 9:05 a.m. Forklift's leaking hydraulic line creates the oil slick. Time. 9:15 a.m. Bob's tire hits the oil.
Wow. So you can see how the different timelines interact and lead to the final event. It really helps you identify those command errors we talked about earlier.
It connects the actions of management directly to the actions of the worker and the failure of the equipment, all on one chart.
So we've used the tools.
Yeah.
We've done the analysis. We found that this wasn't just Bob's fault. It was a combination of command error, the pressure to hurry, a system defect, the oil leak and poor maintenance, and an operating error, Bob speeding. We write the report.
And the investigation isn't done until that report is filed. And crucially, the report must recommend specific, actionable changes. Fix the leak. Install a speed governor on the forklifts. Change the production scheduling policy so workers aren't pressured. If you file a report and nothing changes, you haven't done safety, you've just done paperwork.
This has been a massive download. We've literally gone from, 1930s eugenics, basically, to modern systems engineering and logic trees. What's the big synthesis for you, the main takeaway from this whole journey?
For me, it's the powerful realization that accident is a misnomer. These aren't random events that just happen. They are the logical, inevitable, predictable output of a flawed system. If you have production pressure plus deferred maintenance plus inadequate training plus poor housekeeping, you will have a crash. It is not a question of if, but simply when.
And that realization is actually empowering. Because if it's a system, it means we can re-engineer it. We can fix it.
Exactly. We are not at the mercy of fate or bad luck. We are at the mercy of our own systems, which we have the power to change.
I want to leave everyone with a final thought to chew on. Go back to that safety pyramid. For every one serious injury, there are 600 near misses. So as you are walking through your workplace, or even just walking through your own home and you stumble on a wrinkled rug, or you drop a heavy tool and it almost lands on your foot, stop for a second. Don't just say whoops and move on. Recognize that what just happened was one of your 600 free warnings. That was the system whispering to you that something is wrong. So the question to ask yourself is, how many free warnings is your organization, or even just you, ignoring right now because they seem too small and insignificant to matter?
That is the question that keeps good safety professionals up at night. Are we listening to the whispers before they are forced to become screams?
On that cheery note, thank you for diving deep with us. Start counting those near misses and stay safe out there. We'll see you next time.